welcome to today's webinar. The topic today is analysis of air-supported structures. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the German and English webinars, technical content of the website, and so on. I will be the moderator today and I will answer your questions during the webinar. My colleague Clemens Gutmann will be the presenter today. He's the deputy head of product engineering in our company, and the main responsible person for the development of the add-on form finding and the program RWind. You can ask questions when you press the button with the question mark, then enter your question in that field, press send, and I will receive your question and I will answer you. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. Okay, that's for the moment all from my side. I hand over to Clemens. Clemens, you can start.
Thank you, Andreas, for the introductory words. I also want to welcome you to today's webinar. Today we want to look at air-supported structures, and we're talking about, or going to talk about, four chapters today. So first, I want to briefly introduce you to the fundamentals of air-supported structures. Second, I want to show you a simple model that we can see on the right here. So a simple inflated tube where we are going to discuss these fundamentals on a model. And then we have a more complex structure, an arc structure, for which I want to use our API and show you the capabilities of the API in conjunction with wipe coding. So how can we use the API without knowing too much about programming itself? And then ultimately a quick summary of the discussed topics. So if you talk about these air-supported structures, these are quite a special area, let's say, in the field of membrane design or membrane structures. So normally we have like standard membrane structures like stadium roofs, and then we have pneumatic cushion structures, so ETFE foils or something like that. So they too use like an air support, internal air cushion, but they, in difference to the air-supported structures I want to discuss today, they're not as completely load-bearing. So if you have an ETFE foil, it's somehow embedded in a grid structure or so. But these air-supported structures, for example, bouncy castles or event structures, these are mostly completely driven by this internal pressure. So why am I talking about this? Recently we got an interesting support inquiry about these type of structures, and we wanted to pass on the things we learned here. And so what's the key principle of these air-supported structures? They're air-supported. So the main stability factor of these type of structures is an internal air overpressure. So let's jump into RFEM and let's have a look at the first model. So that's a basic tube, and what are the things that we need to do here? So first of all, of course, we need material for this type of structure. Here we provide materials in the database. The important thing is that it is a material type fabric, because or if you pick a material from the database, which is a membrane material, it will be automatically assigned like this. But of course you can always check here user-defined material and alter these materials, then this material type will be kept. But this has some effect on connected objects, let's say, that behave differently. So make sure that the material type is fabric. And then, of course, we need dry air, which is a gas. Next thing is the thickness. If we, and there's the first effect of what I just mentioned, if we assign a material of type fabric or foil to a thickness, the thickness will automatically be set to 1 millimeter. Why is that? And it's also grayed out. You cannot alter it. Why is that? When dealing with membranes, you usually don't consider the thickness. It's roughly around 1 millimeter anyway, but you rather focus on the width of the material. So it's kilonewtons per meter, for example. So the thickness doesn't really count. So there's a, let's say, ideal thickness that we put in here. Then the next thing is, this is already calculated. So the original topology is a simple tube with caps, and I split the outer surface into 2 parts and then assigned the loads and so on. Of course, we have also the internal solid, which is a gas. Important here is you need some initial condition for that gas. Usually it's like atmospheric pressure, like roughly 1 bar, and some initial temperature if you want to apply temperature loads, that the gas knows what its initial condition is. Next thing is the whole support topic, let's say. So if you look at reality, this thing somehow stands on a meadow or so. Maybe there are some cables attached to it, and you have this surface support. The issue with the surface support is, if we take a look at the deformed structure again, that we have this dome, let's say, and if you assign a surface support to this most likely will lead to instabilities and or calculation convergence issues, because it's quite hard. So normally you would try to assign some nonlinear surface support to this, but this inflicts the whole calculation by a lot. So that's why I chose a different approach. I chose some nodal supports here. One of them is fixed, and the others are fixed in the Z direction, but not in the other planes. There I have a spring. You can also think of a line support maybe. I also recommend trying out the surface support. Maybe it works for your structure, but keep in mind that there might be issues, especially if you try to use the nonlinear behavior of the support. So when the surface lifts up from the ground, that the support is 0. The question is, do you really need it? So in my case, I only want to analyze the structure by itself and not really model this physical complex behavior. But this is one of the findings that we had. Next topic is the mesh. So depending on the size of a structure, you should make sure that you have the correct or appropriate mesh size. So you have this target length for the finite elements will be, which will have an influence on the surface and volume mesh size. But additionally, if I display the mesh, you can see that I applied a line mesh refinement here that to the creases of the tube. Why did I do that? So we found out if the mesh is very coarse and if there are no mesh refinements, this also can lead to calculation issues. Why? Because normally you would manufacture such a tube like this. So you have like the circumference and then the caps, and you put them together like this, and then you inflate them. That means that in reality you will have creases here. Now they're barely visible, but a little bit you can see them here. These, where like the tension fails and there's some compression. And in order to be able to calculate this, it might be necessary, depending on your structure and mesh size, the overall mesh size, that you need some mesh refinements where you have these creases. Then let's have a look at the load cases. Of course, we have a form-finding load case, and then in this case, one additional load case, only a self-weight, that here uses the initial state from the form-finding load case. So this is very important, that all subsequent load cases and also the load combinations, if you have any or create one, any, that they use the initial state. So you have like the form-found state as a basis for further calculations. Then, as I said in the beginning, the only form-finding load that I use here is a solid load. So I don't apply any loads to the surfaces, like you might guess from, like if you do it similar, would think you do it similarly to a normal membrane structure. You can, however, but in reality, you, as I said, manufacture the rough geometry and then you inflate it, and then there will be effects to it, like the creases, like the crease issue that we talked about just before. In my case, I chose a resulting overpressure of 450 Pascal, so that's 0.045 bars, and then I get this result, which looks quite realistic. So that's basically it. Maybe one last comment. If you run into convergence or stability issues, aside from the things that we discussed just now, there are some settings in the static analysis that you can take a look at. So if we look at the form finding, it doesn't make any sense to increase the number of load increments, because then the form finding will run again and again. So if you run into issues, try to increase the number of iterations overall, and also have a look at the form finding settings here. These might help with these issues. Then later, for subsequent load combinations or load cases, depending on the form finding, there it can help to increase the number of load increments depending on your structure. The form finding settings are not of interest anymore, because there's no form finding performed in these subsequent analyses. Then let's have a look at the second structure that I want to discuss today. For this, I took influence from such a finishing line structure as an inspiration. And when preparing this webinar, I thought of how can I model this. There are different approaches. So one approach would be to model such a structure directly in RFEM. That's possible. But then again, I wanted to also do it parametrically. Of course, that's possible as well. So we can define global parameters. But then you have these tubes, and they're intersecting somehow. So what's the second approach that I thought of? Use some external software, Rhino or AutoCAD or so, create the geometry there, and then import it into RFEM and do the analysis. But for this webinar, I chose a different approach, the third one that came to my mind, and that is using our Dlubal API. And since I don't know too much about our Dlubal API, and AI is, everybody's talking about, I wanted to demonstrate what can be done with the vibe coding and the Dlubal API. So also people that are not as familiar with coding can also make use of our very capable API. So what do we need for that? So the prerequisites are, of course, an installed version of RFEM 6 on our PC. The second thing I can show you on our website. So maybe let's switch to English. And if you go here to products, you find our Dlubal API. Sorry, here. And if you click on Discover API, you find basic information, and you find also information about the subscriptions. And here, the important thing for you to know is that you can try out the API for free. You have a certain number of requests. The information can be found, as I said, on the website. And additionally, if you click here on Start with RFEM, you get a documentation where you find all the things if you want to read deeper into this, but it's not really necessary for what I want to show you, because we want to vibe code. So we don't want to write the code ourselves, but use an AI, create the code for us. But this is necessary, so you need a so-called API key. If you go to the extranet, you can create this for free and then you're automatically assigned to this free plan until you hit these limits, and then you are requested to upgrade to a higher tier of the API subscription. But if you want to test it out, you can do that for free. The next thing that we need is somewhere where we can vibe code. So we need an AI. In my case, I chose Claude Code because it's quite capable. And you could install Claude on your desktop and then code within here this program. I chose a slightly different approach. I use a IDE, so a programming interface, because I also want to see the code and do some manual changes maybe later, but it's not really necessary. There are different IDEs. In my case, I'm using PyCharm, which is suitable for everything that has to do with Python, but you can also use Visual Studio Code or any other IDE that is capable of interacting with Python code. And then the next thing to get Claude Code into PyCharm, there's a plugin that you can install for free, and here it then integrates into here the console. And then the last thing that we need is a Python interpreter. So this you can also install on your PC, how you can find on the internet, and then you're good to go. So how do we start? So I prepared a little bit, but I'm going to explain what I want to do, and we're going to see the effects live. So when I start, I here give some background information to the upcoming tasks. So the Claude Code does know some information that it should keep during the tasks, because I'm not going to give a very long prompt, but giving one prompt or some prompts, and then see the effect and try it out, and then go on with the next prompt. So in my case, I say, okay, create a script in a certain folder that I already created for a air inflated arch structure, and I want to use the Dlubal API and RFEM6. And I have a template file that I want to use Claude Code as a starting point, and then I already give the first information. I want to have a 180-degree arc in the XZ plane with a certain diameter, and I want it not as an arc but as a polyline with 7 segments. So this is the first thing. Before we start, maybe let's run this, and then it goes. It searches for the template. It finds the things and reads the files that are inside the folder, and then tries to come up with a first draft. Here you also can see how long it takes. So it's real time. Of course, it takes a while. And then it makes a suggestion of the code. So on the right side, you see the proposed code, and then you can take that over via clicking here, yes, or on the supply button. And then it creates this file. We then can open this file and take a look at it, what it did. So before I start, maybe I can quickly show the template file that I have. So it's really only dummy, let's say, with a skeleton of elements that I created for myself. If you don't know anything about this, you can go to our API documentation, and there you can find some examples for RFEM, for example, here, and you can copy this file, for example, and use this as a basis. So Claude Code, has something to tag along. And so this is the template file that I used, and then you can see here that what it generated. So it automatically imported the Dlubal API. This I forgot. This is also a prerequisite. So if I want to use this IDE, of course, I need to install the API on my PC. So if you don't know how to do that, it's also in the API documentation. Pretty easy to do that. And then, it created the structure, and we then can try this out. So if I lay this side by side here with RFEM, and I can click here the run button, then the script will run. First, it closes all open files, but this is something that is part of the script. So if you don't want to do this, you can remove this line. In my case, it was part of the template file, so it was taken over. And here I can see this polyline that it created with a diameter. I also can see that the geometry parameters are automatically created as a global variable, so I can easily access them and don't have to look through the code. You can tell the AI which parameters you want as parameters and which should be hard-coded, but here the suggestion is fine. So now if I want to change this, and this is the cool thing about using the IDE, you can now change this by yourself without using the AI. So if I want to have 9 and I run the script again, then it will have 9 segments. So that's the first step. And then I can go on with the next prompt. Here I tell, okay, I want a PVC fabric thickness. So I want to see if it finds automatically things in our library, and then I want the API script or the AI to create me a tube around the polyline using membrane quadrangle surfaces in 4 segments, and use arcs for the circumferential lines. So let's see what it does. It's thinking again, looking at the code, and giving us a suggestion how it wants to change the code. So depending on the prompt that you give and the amount of tasks, it can take a while. And then you can see the changes. You can also make a setting that these changes are taken over automatically, but I like to see what it does. So it added some tube radius, it added the segments as a variable, and it created some classes for doing these things. And let's see. Let's click apply, and then put this side by side and run the script again. So as you can see, the script and the API is quite fast. So you can easily double check more or less in real time what the script does in RFEM. So in our case, I can see that the result is pretty nice. What's currently missing are the cap surfaces, for example, and the next things. So but this is the way how you can do it. I don't want to go through the whole process again because it's more or less the same. So you describe in natural language what you want to do. You have to try out a little bit depending on which context you give, which information, the result might be better or worse. So you have to get your hands on and get a feeling for it. How much information do you have to provide in order for the script that is able to run properly, and that you don't have to do too many iterations if you until you get what you actually want. I did this in the preparation phase of this webinar already with a file that I want to show you and discuss with you now. And it took me about, let's say, 40 prompts until I got everything. So I did it in chunks. So you can also think of maybe going in bigger chunks and try if that works. But I was slowly approaching the whole thing because I've never done this before as well. And I was pretty surprised what can be done. So in the end, I got a script with about 600 lines. And I didn't touch any of these lines by myself, aside from maybe adjusting these geometry parameters. I just, coded in natural language, and it also was possible to correct errors. So sometimes things didn't work. So you get not this exit code 0, which is success, but exit code 1, and then you get some error message here in the console, and then I just copied this error message and said, okay, please fix this error. And this also worked. Sometimes it needs one or two approaches, but still it's also easy to deal with error messages in the file using AI. Okay, so maybe let's run the script and see what I did, and then discuss some more things with regard to air-supported structures. All right, so what did I do? So I duplicated the tube one more time. I created some top membrane surfaces and some aprons. I added a member here, cable member. I also added some line supports and nodal supports for the structure. I added the load cases, or let's say the AI added it for me. I just wanted to have them. And yeah, that's basically it. So let's run the script and take a look at the details. So here again, first the form finding load case is run. So that's load case number 1. And then I created some subsequent load cases which are dependent on it. That's why they are starting later on. And then we can see some of the issues that you're highly likely to run into when dealing with these air-supported structures, because they are, let's say, sensitive to the inputs, and I'm going to explain you in a bit why. Calculation has finished. So here the program tells us that there was no instability, but the calculation did not converge. So the form finding load case, it did converge. Maybe let's take a look at the results, or the deformed mesh. That's probably better. Wait, that was the wrong button. So here you can see it looks quite nice. Maybe let's take a look at the loads that I applied. So better visible here. So I added some member load to have some pretension on the cable members. I also added some surface loads here and internal overpressure depending on the structure you're analyzing, you have to play around with the different form finding loads on the different objects. And then you have here the self-weight load case, which did not converge, and you can see why. It's because the membrane, it folds and it gets creases and so on. If we take a look at the results, oh wait, wrong button. Here, which are highly likely not correct, but still you can see some things. So most of the membrane has no tension, and it fails on the compression, so it's unstable, or it's not it's not stable, let's say. How can we cope with that? So the issue that we have, in reality, if I go back to this and this, so in reality, what you would do, you manufacture this geometry like you can see it here. So it's flat, or this tube, for example, is one component, and then you have this second membrane that is stretched across these tubes. And normally, like in the physical world, you would have some contact between the tube and this stretched membrane, and some friction. And while it is quite easy to understand how it works in reality, it's quite difficult to model this using a finite element software, because contact is highly nonlinear topic, and then also the friction is complicated by itself. Then you have the nonlinearity of the material. So it can be done, but again, the most difficult issue is the high deformations. So you can model, of course, contact with friction in RFEM, but in reality you would stretch this membrane over the tubes, and there would be in circumferential direction high deformation that would require that mesh elements reconnect dynamically, and that's not easy to model. So that's probably the issue. I used here some foam finding in the middle, but I did not stretch this also to the or let's say I didn't couple the two cables on the side using this. So this would be the next iteration to try that out, but the rest seems to work. And again, also finding that we had during or that I had during preparing this webinar is also that these form finding loads that you choose, so the solid loads, the surface loads, and the member loads, they all interact with one another, and depending on the structure that you have to play around with them. You can also try this by using AI. Sorry, wrong button here. So you can say to Claude that it should try different parameters and do some optimization runs and rerun the script and read out the error messages from the calculation and try to find suitable load parameters for this. So yeah, just that you know what you have to look at, what are the crucial things when dealing with these types of structures. Another error that you might run into is the error message reading Jacobi matrix error. What does that mean? It means that the mesh is deformed in a way where the calculation cannot proceed. So you have, for example, for a shell element or a plate element, you have a rectangle or a quadratic plane surface, but in reality you don't have this. It's somehow deformed. It's not ideal rectangular, and the let's say mathematical connection between the ideal element definition and the element in the model is defined by this Jacobi matrix. So if the element is deformed in such a way that it cannot be transformed again, the solver throws this error message. So if you run into this issue, you can take a look at the mesh. At the meshing, if the meshing is good, you can take a look at the form finding. So it is of course possible to add form finding loads to a model that don't make a sense or wouldn't work in physical reality. So you have to approach this your issue by playing around with the different parameters that have an influence on this. Yeah, that's basically everything I wanted to show you today. So as a summary, we can say that we learned something about all the different parameters that have an effect on these types of structures. That it is possible to use vibe coding in order to create these types of structures very easily and do them parametrically. The Python script that leads to this model that we discussed just now will be uploaded to the website, so you can take a look and maybe use it as a starting point for your own experiments. I hope that you learned something, and if there are any open questions, I hope you ask them. If you make your own steps, let's say, and you run into issues, feel free to contact our support. We will help you with any issues that you run into, or take a look at our community. And I wish you a pleasant day, and see you next time. And with this, I want to give back to Andreas.
Thank you, Clemens, for your presentation. At the end of the webinar, I have an additional hint to our online courses. There's the RFEM 6 course, that's a course for beginners. Then the Eurocode 2 course for the concrete design with RFEM 6. The Eurocode 3 course for the steel design. The Eurocode 5 course for the timber design. And the Eurocode 8 course for the earthquake design. For more information and prices, just scan the QR codes or click at the links here. You can get such a course for free when you submit your customer project, and after the publishing, you will get one of the courses. The courses are valued at 199 to 399 euros. Just click at the link here or scan the QR code, and you will reach a form on our website where you can upload your files. Then into our free online services, for example, the Dlubal community, you can ask questions there, and they will be answered by other users or our support team. Then there's the GeoZone tool for the determination of snow, wind, and earthquake loads. You can determine cross-section properties. You can download 3D models, for example, as a template for your project. Then there's the 90-day trial version of 6, R-Stub 9, R-Wind3, or R-Section. Just try it. You can get more information on our website, dlubal.com. For example, the recorded webinars. Then, for example, the knowledge base articles. You can ask our AI assistant Mia 24/7, all the day and all the night. Yeah, just try it. Okay, that should be also all from my side. I thank you for your attention. Thanks again to Clemens for the presentation. I wish you all a nice rest of the day. See you. Bye-bye.